Hello and welcome to Bedtime Science. Before we begin, take a moment to like the video, subscribe to the channel, and let me know in the comments where you're watching or listening from tonight. Whether you're tuning in from a quiet city apartment, a countryside home, or somewhere far away under a different sky. It's interesting to think that, at the deepest level, the same strange quantum rules are quietly shaping everything around you, no matter where you are. Tonight, we're going to explore a question that has puzzled scientists for over a century. What makes quantum physics so weird? At first glance, the world feels stable and predictable. Objects sit where we leave them. Causes lead to effects. Reality seems solid, continuous, and reliable. But beneath this familiar surface, far beyond what we can see, exists a very different kind of world. A world where particles can behave like waves, where outcomes are governed not by certainty, but by probability, where something can exist in multiple states at once, and where two particles separated by vast distances can remain mysteriously connected. These ideas don't just stretch our imagination, they seem to break it. And yet, they're not speculative. They've been tested, measured, and confirmed again and again in laboratories across the world. So tonight, as you settle in and relax, we'll gently move away from the solid ground of everyday experience and step into a deeper layer of reality. A layer that doesn't quite behave the way we expect, but may be closer to the true nature of the universe than anything we encounter in daily life. We'll explore how these strange ideas first emerged, why they challenged even the greatest scientific minds, and why, even today, no one fully agrees on what they truly mean. But there's no need to rush. No need to force understanding. Instead, just let the ideas unfold slowly and allow yourself to sit comfortably with the mystery, because sometimes the most fascinating part of science is not having all the answers. If you take a moment to look around you right now, everything seems reassuringly solid. The surface beneath you feels stable, objects stay where they are placed, time appears to move steadily forward, one moment following the next in a predictable sequence. This is the world we're used to, the one our senses have evolved to understand. For centuries, this sense of order was captured beautifully by classical physics, most famously through the work of Isaac Newton. His laws of motion and gravity described a universe that behaved like an intricate, well-designed machine. If you knew the position and motion of every object, you could, at least in principle, predict what would happen next. It was a comforting idea. The universe was understandable, logical, and consistent. But as scientists began to look closer, far closer than the eye could ever see, this picture started to unravel. At scales smaller than atoms, in the realm of electrons and photons, the rules begin to shift in subtle but profound ways. This is where quantum physics emerges. It is not a different universe, but a deeper layer of the same one, operating beneath the surface of everything we experience. Quantum physics is the framework that describes how nature behaves at these extremely small scales. And almost immediately, it presents us with something unusual. The more precisely we try to describe what's happening, the less it resembles anything from our everyday experience. Particles do not behave like tiny billiard balls. Light does not behave like a simple wave. Instead, both seem to blur between categories, taking on properties that resist clear definition. This is often where people begin to describe quantum physics as strange, or even bizarre. But it is worth pausing for a moment and asking a slightly different question. Is the quantum world truly strange, or is it simply unfamiliar? After all, our intuition is shaped by the environment we live in. We are used to objects that are large enough to see, touch, and interact with directly. We do not naturally experience the behavior of individual electrons or photons. So perhaps what feels strange is not the behavior itself, but the way it clashes with expectations built for an entirely different scale. To get a sense of just how different these scales are, consider the size of an atom. If you were to magnify a single atom until it was the size of a large stadium, the nucleus at its center would still be no larger than a small marble. The electrons would exist as a diffuse region spread across the entire space, not as tiny orbiting dots, but as something far less defined. Already the familiar picture begins to dissolve. In this microscopic domain, certainty gives way to probability. Instead of saying where a particle is, we begin to talk about where it is likely to be. Instead of following a single clear path, particles can explore many possibilities at once. And instead of being isolated, they can become deeply connected to one another in ways that seem to ignore distance entirely. These are not just abstract ideas. They are grounded in experiments that have been repeated and refined over decades by research groups across the world, from early laboratories in Europe to modern facilities such as CERN. And yet, despite this strong experimental foundation, there is still something about quantum physics that resists easy interpretation. One reason for this may lie in the way we think about reality itself. In classical physics, objects are assumed to have definite properties. A ball has a position and a velocity whether or not anyone is looking at it. The world exists independently, and observation simply reveals what is already there. Quantum physics challenges this assumption in subtle but important ways. Some interpretations suggest that the properties of a system do not exist in a fully defined way until they are measured. Others propose that what we call reality is not a fixed structure, but something that emerges through interactions. This is where the work of Carlo Rovelli becomes especially interesting. His approach, known as relational quantum mechanics, suggests that the properties of an object are not absolute, but relative to other objects. In this view, there is no single universal description of reality, and instead, reality is made up of relationships between systems. It is a shift that feels almost philosophical. Rather than asking what something is, we begin to ask how it relates to something else. This idea may sound abstract at first, but it offers a different way of thinking about the apparent weirdness of quantum physics. If reality is fundamentally relational, then the strange behaviors we observe may not be contradictions at all. They may simply reflect a deeper structure that does not align with our everyday expectations. And this brings us back to the question of perception. Our senses are not designed to reveal the true nature of reality in all its detail. They are designed to help us survive. They present us with a simplified version of the world, one that is stable, continuous, and easy to navigate. At larger scales, this simplified picture works remarkably well. But at smaller scales, it begins to lose its accuracy. It is a little like looking at a digital image. From a distance, everything appears smooth and seamless. But as you zoom in, the image breaks down into individual pixels, each with its own distinct value. The closer you look, the less the image resembles what you first saw. Quantum physics may be revealing something similar about the universe. What appears smooth and continuous at one scale may be far more complex and subtle at another, and perhaps this is why it feels so unfamiliar. Not because it is illogical, but because it operates according to principles that lie outside our usual frame of reference. As we continue, it can be helpful to let go of the need for everything to make immediate sense. Quantum physics is not something that can always be forced into familiar categories. Instead, it often requires a different kind of understanding, one that is comfortable with uncertainty, open to multiple possibilities, and willing to accept that some questions may not have simple answers. There is a quiet beauty in that, a reminder that the universe is not obligated to match our expectations. And as we move deeper into this hidden layer of reality, we begin to see that what we call weirdness may not be a flaw in the theory at all. It may be a sign that we are finally seeing the universe as it truly is, not as we once imagined it to be. For a long time, the universe appeared to follow a simple and reassuring rule. If you knew how something was moving now, you could predict where it would be later. This idea is known as determinism, and it sits at the very heart of classical physics. In this view, the future unfolds from the present with perfect continuity, like a set of carefully arranged dominoes falling one after another. Each event has a clear cause, and each cause leads to a predictable effect. It is a picture of reality that feels orderly and dependable, and for everyday experiences it works remarkably well. But even within this seemingly stable framework, small hints began to emerge that something was not quite as certain as it appeared. One of the first to notice this was the French mathematician and physicist Henri Poincaré. In the late 19th century, while studying systems like the motion of planets, he discovered that even simple systems could behave in ways that were extremely sensitive to initial conditions. A tiny difference in starting position could lead to dramatically different outcomes over time. This insight became one of the early foundations of what we now call chaos theory. It revealed that predictability has limits, even within classical physics, not because the laws themselves are uncertain, but because the systems they describe can become too complex to track precisely. Imagine trying to predict the exact path of a single leaf falling through the air. In principle, the motion follows clear physical laws, But in practice, every tiny gust of wind, every subtle shift in air pressure, influences the outcome. The system becomes so sensitive that long-term prediction becomes nearly impossible. Poincaré's work quietly suggested that determinism might not be as absolute as it once seemed. The universe could still follow precise laws, yet remain unpredictable in practice. Still, this was only a small crack in an otherwise solid structure. A far more dramatic challenge emerged when physicists began studying something as seemingly simple as heat and light. At the end of the 19th century, scientists were trying to understand how objects emit radiation when they are heated. This type of radiation is known as blackbody radiation. A blackbody is an idealized object that absorbs all incoming light and re-emits energy depending on its temperature. The problem seemed straightforward. Using classical physics, researchers attempted to calculate how much energy would be emitted at different wavelengths. But when they carried out the calculations, they encountered a strange and troubling result. The equations predicted that as the wavelength of light became shorter, moving toward the ultraviolet region, the energy emitted would increase without limit. In other words, a hot object should release an infinite amount of energy at very short wavelengths. This prediction became known as the ultraviolet catastrophe. It was not just a minor error. It was a complete breakdown of the theory. In reality, objects do not emit infinite energy. The classical equations were clearly missing something fundamental. This is where Max Planck enters the story. In the year 1900, Planck approached the problem with a bold and somewhat reluctant idea. He proposed that energy is not emitted continuously, but in discrete packets, which he called quanta. Instead of energy flowing smoothly, it comes in small, indivisible amounts. This idea can be expressed in a simple relationship. The energy of a quantum is equal to a constant multiplied by the frequency of the radiation. In words, this is energy equals Planck's constant multiplied by frequency. Planck's constant is an extremely small number, approximately 6.63 times 10 to the minus 34 joule-seconds. Its small size explains why quantization is not noticeable at everyday scales, but at atomic and subatomic levels it becomes essential. At first, Planck treated this idea as a mathematical trick, a way to fix the equations rather than a description of reality. But as time went on, it became clear that this quantization was not just a convenient assumption. It was pointing toward a deeper truth about how nature behaves. Energy, it seemed, is fundamentally granular. This was a turning point. The smooth, continuous world described by classical physics was beginning to give way to something more structured, yet less intuitive. Around the same time, other scientists were exploring related questions, and the sense of certainty continued to fade. In the 20th century, the chemist and physicist Ilya Prigogine studied systems far from equilibrium, such as chemical reactions and thermodynamic processes. His work focused on irreversibility, the idea that certain processes naturally move in one direction and cannot simply be reversed. A broken cup does not spontaneously reassemble itself. Heat flows from hot objects to cold ones, not the other way around. These processes introduce a direction to time, often referred to as the arrow of time. Prigogine showed that systems could evolve in complex and sometimes unpredictable ways, especially when they are driven away from equilibrium. Order could emerge from disorder, and small fluctuations could grow into large-scale structures. This added another layer of complexity to our understanding of nature. Even when the underlying laws are known, the behavior of systems can be difficult to predict, and sometimes impossible to reverse. Taken together, these developments began to reshape the picture of reality. Classical physics was not wrong. It still describes the motion of planets, the trajectory of falling objects, and the behavior of everyday materials with remarkable accuracy. But it was becoming clear that it was not the whole story. Instead, it appeared to be an approximation, a simplified model that works well at larger scales, but begins to break down as we look more closely. Quantum theory emerged not as a contradiction to classical physics, but as a deeper layer beneath it. Where classical physics assumes continuity, quantum physics introduces discreteness. Where classical physics relies on certainty, quantum physics allows for probability. Where classical physics describes definite states, quantum physics opens the door to possibilities. This transition from certainty to uncertainty can feel unsettling at first. It is natural to want clear answers, precise predictions, and a stable sense of reality. But as physics has progressed, it has revealed that the universe does not always conform to these expectations. Instead, it invites us to think in new ways, to accept that not everything can be predicted with absolute precision, to recognize that some processes are inherently probabilistic, and to understand that the deeper we look, the more subtle and nuanced the behavior of nature becomes. There is something quietly humbling about this shift. The universe, it seems, is not a perfectly predictable machine. It is something richer, more complex, and perhaps more interesting than that. And as we continue to explore these ideas, the initial cracks in classical physics begin to widen, revealing an entirely new way of understanding reality. One that is less certain, but far more intriguing. By the early years of the 20th century, physics had reached an unusual moment. The foundations of classical theory were still standing, but they were no longer entirely secure. Small inconsistencies had begun to appear, and each attempt to resolve them seemed to introduce even deeper questions. What followed was not a single breakthrough, but a gradual and often confusing transformation. The birth of quantum theory did not arrive as a clear, unified idea. It emerged piece by piece, shaped by a series of discoveries that did not always agree with one another. At the center of this transformation was Max Planck. As we have already seen, Planck introduced the idea that energy is emitted in discrete packets, or quanta, while studying blackbody radiation. At the time, he viewed this as a mathematical solution rather than a statement about physical reality. In fact, Planck himself was deeply committed to classical ideas, and he was not particularly comfortable with the implications of his own proposal. Yet his work introduced a constant, now known as Planck's constant, that would quietly become one of the most important numbers in all of physics. Its value, approximately 6.63 times 10 to the minus 34 joule-seconds, sets the scale at which quantum effects become significant. It is such a small number that its influence is almost invisible in everyday life, but at atomic scales, it governs how energy is exchanged, how particles behave, and how systems evolve. If Planck opened the door, it was Albert Einstein who stepped through it with unexpected confidence. In the year 1905, often referred to as Einstein's miracle year, he published a series of papers that would reshape physics in multiple ways. Among them was his explanation of the photoelectric effect. This phenomenon occurs when light shines on a metal surface and causes electrons to be ejected. Classical wave theory predicted that increasing the intensity of light should increase the energy of the emitted electrons. But experiments showed something different. No matter how intense the light was, if its frequency was below a certain threshold, no electrons were emitted at all. And when electrons were emitted, their energy depended not on the intensity of the light, but on its frequency. Einstein proposed a bold explanation. Light itself, he suggested, is made up of discrete packets of energy, which we now call photons. Each photon carries energy according to the relationship energy equals Planck's constant multiplied by frequency. This idea was deeply unsettling. Light had long been understood as a wave, a continuous oscillation spreading through space. Now, Einstein was suggesting that it also behaves like a collection of particles. Even more surprisingly, it was this work, rather than his theory of relativity, that later earned him the Nobel Prize. Einstein himself would go on to have a complicated relationship with quantum theory. While he helped establish its foundations, he remained uneasy with its implications, particularly its reliance on probability. But at this stage, the focus was not yet on interpretation. It was on making sense of experimental results that refused to fit into existing frameworks. Another key figure in this evolving story was Niels Bohr. Bohr turned his attention to the structure of the atom, specifically the hydrogen atom, which consists of a single electron orbiting a single proton. Classical physics predicted that an electron moving in a circular orbit should continuously emit radiation, losing energy and spiraling into the nucleus in a very short time. But atoms are stable. They do not collapse in this way. To resolve this contradiction, Bohr proposed a new model in which electrons can only occupy specific, quantized energy levels. These levels are like discrete steps rather than a continuous range. An electron can move between these levels, but it cannot exist in between them. When it jumps from a higher energy level to a lower one, it emits a photon of light with a specific energy. This model successfully explained the spectral lines of hydrogen, which had been observed experimentally but not fully understood. Each spectral line corresponds to a transition between energy levels, producing light at a precise frequency. Bohr's model was a remarkable step forward, but it was also incomplete. It combined classical and quantum ideas in a way that worked for simple systems but could not easily be extended to more complex atoms. Still, it introduced a crucial concept. Energy levels in atoms are not continuous, they are quantized. As these ideas began to spread, new contributors entered the picture, each adding their own perspective. One of them was Satyendra Nath Bose, an Indian physicist whose work would have a lasting impact on quantum theory. In the early 1920s, Bose developed a new way of counting the possible states of particles, particularly photons. Instead of treating particles as distinguishable entities, he considered them indistinguishable, meaning that swapping two identical particles does not create a new configuration. This seemingly subtle change led to a new type of statistical behavior, now known as Bose-Einstein statistics. Bose sent his work to Einstein, who immediately recognized its significance and helped publish it. Einstein then extended these ideas to atoms, predicting the existence of a new state of matter, now called a Bose-Einstein condensate. In this state, particles occupy the same quantum state and behave as a single, unified system. Although this phenomenon was not experimentally observed until many decades later, it remains one of the most striking examples of quantum behavior on a macroscopic scale. While these breakthroughs were unfolding, another important figure was quietly shaping the next generation of physicists. Arnold Sommerfeld, a German physicist, expanded on Bohr's atomic model and introduced more sophisticated mathematical techniques. But perhaps his greatest contribution was his role as a teacher. Sommerfeld mentored a remarkable group of students, including Werner Heisenberg and Wolfgang Pauli, who would go on to play central roles in the development of quantum mechanics. In this way, the birth of quantum theory was not just a series of individual discoveries. It was also a collaborative process, shaped by networks of scientists sharing ideas, challenging assumptions, and building on each other's work. And throughout this process, one theme appears again and again: confusion. The early pioneers of quantum theory were not guided by a clear vision of what the final theory would look like. They were responding to experimental results that did not make sense within existing frameworks. Each new idea solved one problem, but often introduced another. Light behaves like a particle, but also like a wave. Electrons occupy discrete energy levels, but also seem to spread out in space. Particles are indistinguishable, yet still produce measurable effects. It was not a neat or orderly progression. It was a process of trial, error, and gradual refinement. And yet, despite this apparent disorder, a coherent theory began to emerge. By the mid-1920s, the foundations of quantum mechanics were being established through the work of scientists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Their formulations provided a consistent mathematical framework that could describe a wide range of phenomena with remarkable accuracy. This new theory did not resemble classical physics. It did not offer simple, visualizable models. Instead, it relied on abstract mathematical structures and probabilistic predictions. But it worked. It explained atomic spectra, chemical bonding, and the behavior of electrons in solids. It laid the groundwork for technologies that would later transform the world, from semiconductors to lasers. And it all began with a series of small cracks in classical understanding. What is perhaps most striking about this story is not just the ideas themselves, but the way they emerged. Not from certainty, but from uncertainty. Not from clarity, but from contradiction. Quantum theory was not discovered in a single moment. It was assembled piece by scientists who were willing to question deeply held assumptions and follow the evidence wherever it led, even when that path led into unfamiliar territory. And as these early developments began to settle into a more complete framework, the stage was set for an even deeper exploration of the quantum world, one that would challenge not just our understanding of physics, but our understanding of reality itself. At some point, as physicists explored deeper into the behavior of light and matter, a quiet but profound question began to take shape. What exactly is a particle? It sounds like a simple thing. A particle is something small, localized, and discrete. It has a position. It follows a path. It exists in one place at a time, and a wave, by contrast, is something extended and spread out. It oscillates. It interferes with itself. It does not travel along a single, well-defined trajectory. For a long time, these two categories seemed completely separate. Particles were one kind of thing, waves were another. The distinction felt clear and dependable. But in the early 20th century, that distinction began to dissolve. One of the most striking demonstrations of this comes from a deceptively simple setup known as the double slit experiment. Imagine a barrier with two narrow openings, placed between a source of particles and a detection screen. If you fire small objects like tiny grains of sand through the slits, you would expect each grain to pass through one slit or the other and land on the screen behind. Over time, you would see two clusters forming on the screen, each aligned with one of the slits. This is exactly what classical intuition predicts. Now, if instead of grains of sand you send waves through the slits, such as water waves or light waves, something different happens. The waves spread out after passing through the openings and begin to overlap. Where the peaks of one wave align with the peaks of another, they reinforce each other, creating a bright region. Where peaks align with troughs, they cancel out, creating a dark region. The result is an interference pattern, a series of alternating bands of high and low intensity. So far, everything behaves as expected. But now comes the surprising part. When physicists perform this experiment with particles like electrons, something unusual occurs. If you send many electrons through the slits, one at a time, and record where they land, the pattern that gradually builds up on the screen is not two simple clusters. It is an interference pattern. This suggests that each electron is somehow behaving like a wave, passing through both slits at once and interfering with itself. And yet, when an individual electron is detected, it appears as a single, localized point on the screen, as if it were a particle. It is not spread out. It does not leave a faint trace across multiple locations. It arrives at one specific place. So which is it? Is the electron a wave or a particle? The answer, according to quantum mechanics, is that it is both, and neither, depending on how it is observed. This phenomenon is known as wave-particle duality. It is not simply that particles sometimes act like waves and sometimes like particles. It is that the underlying reality does not fit neatly into either category. The behavior we observe depends on the experimental setup, on how we choose to measure the system. If we design the experiment to detect which slit the electron passes through, the interference pattern disappears and the electron behaves more like a particle. If we do not measure its path, the interference pattern returns and the electron behaves more like a wave. This raises a deeper question. What is the electron doing when it is not being observed? Is it truly passing through both slits at once? Is it following a path we simply cannot detect? Or is the question itself not well defined? In the early 1920s, a young physicist named Louis de Broglie proposed a bold idea that helped to frame this puzzle in a new way. If light, which had been understood as a wave, could behave like a particle, perhaps matter, which had been understood as particles, could behave like waves. De Broglie suggested that every particle has an associated wavelength determined by its momentum. In words, this relationship can be expressed as wavelength equals Planck's constant divided by momentum. This idea was initially met with skepticism, but it soon found experimental support. In experiments conducted by Clinton Davison and Lester Germer in the United States, and independently by George Paget Thompson in England, electrons were shown to produce interference patterns when scattered from crystals. These experiments confirmed that matter does indeed exhibit wave-like properties. The implications were profound. It was no longer possible to think of particles as simple, localized objects. They had an extended, wave-like aspect that could not be ignored. And yet, they still produced discrete, particle-like outcomes when measured. This duality lies at the heart of quantum mechanics, and it is one of the main reasons the theory feels so unfamiliar. To make sense of this, some physicists explored alternative ways of thinking about what might be happening beneath the surface. One such approach was developed by David Bohm in the mid-20th century. Bohm proposed what is known as pilot wave theory, or the de Broglie-Bohm interpretation. In this framework, particles always have definite positions and follow precise trajectories, but their motion is guided by a wave. This guiding wave evolves according to the same mathematical rules as the wave function in standard quantum mechanics. It influences the motion of the particle in a way that produces the observed interference patterns. In this picture, the electron does not split into multiple paths. Instead, it follows a single path, while the guiding wave passes through both slits and shapes the outcome. It is a more intuitive model in some ways, restoring a sense of underlying structure and continuity. However, it comes with its own challenges, including the need for non-local interactions, where changes in one part of a system can instantaneously influence another. Despite these challenges, Bohm's theory remains an important reminder that quantum mechanics can be interpreted in different ways, each offering its own perspective on the same underlying phenomena. And this brings us back to the question of categories. Perhaps the difficulty lies not in the behavior of particles, but in the concepts we're using to describe them. The words particle and wave come from our everyday experience. They are useful for describing objects and phenomena at scales we can directly observe. But at the quantum level, these categories may no longer apply. Instead of trying to force quantum systems into familiar labels, it may be more accurate to think of them as something entirely new, something that shares properties with both particles and waves, but is not fully captured by either. In modern quantum mechanics, this idea is formalized through the concept of the wave function, a mathematical object that encodes the probabilities of different outcomes. The wave function evolves smoothly, like a wave, but when a measurement is made, it produces discrete results, like particles. It is not that the electron is switching back and forth between being a wave and being a particle. It is that our descriptions are limited, and the underlying reality does not fit neatly into the categories we have inherited. There is a quiet shift that happens here. Instead of asking what something is, we begin to ask how it behaves under different conditions. This shift may seem subtle, but it changes the way we think about reality, and it introduces a deeper sense of mystery. Because if the basic building blocks of the universe do not conform to clear, intuitive categories, then perhaps our understanding of reality needs to be more flexible as well. What initially appears as strangeness may simply be the result of looking at the world from the wrong perspective. And as we continue to explore these ideas, the boundaries between familiar concepts begin to soften, revealing a landscape that is less rigid, but far more intriguing than we might have imagined. If there is one experiment that quietly sits at the heart of quantum physics, it is the double-slit experiment. On the surface, it is remarkably simple. A source emits particles. A barrier contains two narrow openings. Beyond the barrier, a screen records where those particles arrive. It is the kind of setup that could be sketched on a piece of paper in just a few lines. And yet this simple arrangement reveals something deeply unexpected about the nature of reality. To understand its full significance, it helps to move slowly, step by step, through what actually happens. Imagine first that we are sending individual electrons toward the barrier, one at a time. Not a continuous stream, but a sequence of single particles spaced far enough apart that they cannot interact with one another. If electrons were behaving like classical particles, each one would pass through either the left slit or the right slit, and we would expect to see two distinct regions forming on the detection screen over time. But that is not what happens. Instead, as more and more electrons are detected, a pattern begins to emerge. At first, the screen shows scattered individual impacts, each one appearing as a small localized point. But gradually, these points arrange themselves into a series of alternating bands, bright regions where many electrons arrive, and dark regions where almost none do. This is an interference pattern. What makes this so striking is that the pattern builds up, even though the electrons are sent one at a time. Each electron seems to contribute a single point, yet collectively they form a structure that suggests wave-like behavior. It is as if each electron is somehow aware of both slits, even though it passes through the apparatus alone. This is what is meant by single particle interference. Each electron behaves in a way that cannot be explained by choosing one path or the other. Instead, it appears to explore multiple possibilities simultaneously, and the interference pattern reflects the combination of those possibilities. To describe this behavior, quantum mechanics uses the concept of probability amplitudes. These are mathematical quantities associated with different possible paths. When these amplitudes are combined, they can reinforce or cancel each other, producing the familiar pattern of bright and dark regions. The probability of detecting an electron at a particular location is related to the square of the total amplitude at that point. In words, this can be expressed as probability equals the square of the wave function amplitude. While this may sound abstract, it has very concrete consequences. It determines exactly where electrons are more likely to be detected and where they are unlikely to appear. But the story becomes even more intriguing when we try to observe what the electron is doing as it passes through the slits. If we place a detector near the slits to determine which path the electron takes, the interference pattern disappears. Instead, the distribution on the screen changes to two broad clusters, consistent with particle-like behavior. The act of measuring which slit the electron passes through seems to alter the outcome. This is not due to any mechanical disturbance in the usual sense. Even very gentle measurements, designed to minimize interaction, produce the same effect. The presence or absence of information about the path changes the result. This leads to a subtle but important idea. It is not just the physical setup that matters, but the information that can be obtained from it. In the mid-20th century, the physicist John Archibald Wheeler explored this idea further through what he called delayed choice experiments. In these experiments, the decision to observe which path the particle takes is made after the particle has already passed through the slits, but before it is detected on the screen. This raises a curious possibility. If the outcome depends on whether we choose to measure the path, and that choice is made after the particle has passed the slits, it seems as though the behavior of the particle is influenced by a future decision. Of course, it is not that the future is literally reaching back in time, but the experiment challenges our usual assumptions about cause and effect. It suggests that the distinction between wave-like and particle-like behavior is not determined solely at the moment the particle passes through the slits. Instead, it depends on the entire experimental context, including how the system is ultimately measured. Wheeler himself summarized this idea with a striking phrase. He suggested that no phenomenon is a phenomenon until it is an observed phenomenon. In other words, what we observe is not simply revealing a pre-existing reality. It is part of the process that defines that reality. This perspective becomes even more pronounced when we consider modern developments in quantum information. Physicists such as Anton Zeilinger have emphasized that information plays a central role in quantum mechanics. In this view, the properties of a system are closely tied to the information that can be obtained about it. Zeilinger and his colleagues have conducted experiments involving entangled photons, demonstrating that quantum systems can be understood in terms of information correlations rather than independent physical properties. In one sense, this shifts the focus of physics. Instead of asking what a system is, we begin to ask what can be known about it and how that knowledge is structured. This does not mean that reality disappears or becomes purely subjective. The outcomes of experiments are still objective and reproducible, but it does suggest that the act of measurement and the information it provides is deeply woven into the fabric of quantum phenomena. Returning to the double-slit experiment, we can begin to see it in a slightly different light. The presence of an interference pattern indicates that no information is available about which path the particle took. The system retains multiple possibilities, and these possibilities combine to produce the observed pattern. When path information becomes available, even in principle, those possibilities no longer combine in the same way. The interference disappears, and the system behaves as if a single path has been selected. It is not simply that the particle changes its behavior, it is that the structure of possibilities and the information associated with them has changed. This idea can feel subtle and perhaps a little unsettling. We are used to thinking of reality as something that exists independently, waiting to be discovered. But in quantum mechanics, the distinction between what exists and what can be known becomes less clear. There is a gentle shift from thinking about objects to thinking about relationships, from focusing on what is happening to focusing on what can be measured. And while this may seem abstract, it is grounded in precise experimental results. The double-slit experiment has been performed with electrons, photons, atoms, and even large molecules composed of dozens of atoms. In each case, the same fundamental behavior appears: interference when paths are indistinguishable, no interference when path information is available. This consistency across different systems suggests that the underlying principle is not limited to a specific type of particle. It is a general feature of the quantum world. There is also a quiet elegance in this. A simple experiment, repeated in different forms, revealing the same underlying pattern. It is almost as if the universe is gently pointing toward a deeper truth, one that is not immediately obvious, but becomes clearer the more closely we look. And perhaps this is where the sense of weirdness begins to deepen. Not because the experiment is complicated, but because its implications are so difficult to reconcile with everyday intuition. A single particle interfering with itself, outcomes shaped by what can be known, behavior that depends on the structure of information. These ideas do not fit easily into familiar categories, but they do fit the data, and in physics, that is what matters most. As we continue to explore these concepts, it becomes increasingly clear that the quantum world is not just a smaller version of the classical one. It is something fundamentally different, where the act of observation and the flow of information are not just passive elements, but active participants in the unfolding of reality. As the picture of the quantum world began to take shape, one idea quietly moved to the center of everything. Not certainty, but probability. In classical physics, probability usually reflects a lack of knowledge. If you roll a die and do not know how it will land, you describe the outcome in terms of chances. But in principle, if you knew every detail about the force of the throw, the angle, the air resistance, and the surface it lands on, you could predict the result exactly. The randomness is practical, not fundamental. Quantum physics introduces a very different kind of uncertainty. Even with complete knowledge of a system, there are limits to what can be predicted. These limits are not due to measurement errors or missing information. They are built into the structure of the theory itself. This idea was made precise by Werner Heisenberg in the late 1920s through what is now known as the uncertainty principle. The uncertainty principle states that certain pairs of physical properties cannot both be known with arbitrary precision at the same time. The most well-known example involves position and momentum. Momentum in this context refers to the product of mass and velocity. It tells us how much motion an object has. Heisenberg's principle can be expressed in words as follows. The uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to a small constant, equal to Planck's constant divided by 4 times pi. This may sound technical, but its meaning is surprisingly clear. If you try to measure the position of a particle very precisely, the uncertainty in its momentum increases. If you try to measure its momentum very precisely, the uncertainty in its position increases. There is no way around this. It is not a limitation of our instruments, it is a feature of nature itself. To get a sense of scale, Planck's constant is extremely small, which means that these uncertainties are negligible for large objects. For something like a tennis ball, the effect is so tiny that it can safely be ignored. But for an electron, which has a mass of about 9.1 times 10 to the minus 31 kilograms, these uncertainties become significant. At that scale, position and momentum cannot both be sharply defined. This leads to a shift in how we describe physical systems. Instead of specifying exact values, we describe a range of possible outcomes, each with a certain probability. The wave function, introduced earlier, provides a way to calculate these probabilities. If we want to know where an electron is likely to be, we do not assign it a single position. We describe a probability distribution, a spread of possible locations, each with its own likelihood. When a measurement is made, a specific outcome is observed, but the theory itself only predicts the probabilities of different outcomes, not which one will occur in any individual case. This can feel like a loss of certainty. But it is also a gain in accuracy. Quantum mechanics does not tell us exactly what will happen in a single event, but it tells us precisely how often different outcomes will occur over many repetitions. And these predictions have been confirmed to an extraordinary degree of precision in experiments around the world. Still, the question remains, what does this probability actually represent? Is it a reflection of something real in the world, or is it simply a description of our knowledge? This question has led to a range of interpretations, each offering a slightly different perspective. One particularly interesting approach is known as quantum Bayesianism, or cubism, developed in part by the physicist Christopher Fuchs. In cubism, probability is not seen as an objective property of a system. Instead, it represents an agent's personal degree of belief about the outcome of a measurement. In this view, the wave function does not describe an external reality. It encodes expectations about future experiences. When a measurement is made, the outcome is not the revelation of a pre-existing value, but the creation of a new experience. The probabilities reflect how an observer updates their expectations based on prior information. This interpretation shifts the focus from the system itself to the relationship between the observer and the system. It suggests that quantum mechanics is not just a theory about physical objects, but also a framework for organizing knowledge and expectation. Not everyone agrees with this perspective. Other interpretations treat probability as something more objective, built into the fabric of reality itself. In these views, randomness is fundamental. When a quantum event occurs, such as the decay of a radioactive atom or the detection of a photon, the specific outcome is genuinely unpredictable. There is no hidden detail, no underlying variable that determines the result in advance. It simply happens within the constraints set by the probability distribution. This raises a subtle but important distinction. Is randomness something that exists in the world, or is it something that exists in our description of the world? In classical physics, randomness is usually epistemic, meaning it reflects a lack of knowledge. In quantum physics, it may be ontological, meaning it reflects the nature of reality itself. To illustrate this, consider a simple example. Imagine a particle prepared in a state where it has an equal probability of being detected in one of two locations. When a measurement is made, the particle is found in one location or the other. If we repeat the experiment many times, we will find that each location is detected about half the time. The probabilities are clear and consistent, but for any single measurement, the outcome cannot be predicted in advance. This is not due to experimental limitations, it is a fundamental feature of the theory. There is something quietly profound about this. The universe, at its most basic level, may not be fully determined. Instead of a single, fixed future unfolding from the present, there may be a range of possible futures, each with its own probability, and the act of measurement selects one of these possibilities. This does not mean that anything can happen. The probabilities are tightly constrained by the mathematical structure of quantum mechanics. But within those constraints, there is room for genuine unpredictability. For some, this idea is unsettling. It challenges the notion of a clockwork universe, where everything follows a predetermined path. For others, it introduces a different kind of beauty, a universe that is not rigidly fixed but open in subtle ways, a universe where outcomes are not fully decided until they occur, and perhaps a universe that is a little less mechanical and a little more dynamic than we once imagined. As these ideas settle in, the sense of quantum strangeness begins to deepen. Not because the theory is inconsistent, but because it asks us to let go of assumptions that have guided our thinking for centuries. Certainty gives way to probability, precision gives way to distributions, prediction gives way to likelihood. And in that shift, we begin to see that uncertainty is not a flaw in our understanding. It is part of the structure of reality itself. As quantum theory continued to develop, something else began to stand out, something that felt almost as strange as the behavior it was trying to describe. The mathematics worked extraordinarily well. In fact, it worked so well that it often seemed to understand the quantum world more clearly than any physical picture we could form in our minds. At the center of this mathematical framework is a concept introduced by Erwin Schrödinger in the year 1926. He proposed a way to describe quantum systems using what is now called the wave function. The wave function is not a wave in the usual sense. It does not ripple through space like water or sound. Instead, it is a mathematical object that encodes all the possible outcomes of a system. If we want to know where a particle might be found, the wave function provides a distribution of probabilities. If we want to know how the system evolves over time, the wave function changes according to a specific rule, known as the Schrödinger equation. This equation can be described in words as follows. The rate of change of the wave function over time is determined by the total energy of the system, including both kinetic energy and potential energy. It is a compact and elegant relationship, yet its implications are vast. By solving the Schrödinger equation for a given system, physicists can predict how that system behaves. They can determine the allowed energy levels of atoms, the structure of molecules, and the behavior of electrons in materials. And these predictions are not vague approximations. They are precise, often matching experimental results to many decimal places. For example, the energy levels of the hydrogen atom can be calculated with extraordinary accuracy, allowing us to predict the exact frequencies of light emitted during electronic transitions. These predictions have been confirmed through spectroscopy experiments conducted in laboratories across the world. This raises an interesting question. Why does mathematics work so well? Why should abstract symbols and equations developed through human reasoning align so closely with the behavior of the physical world? This question was explored by the physicist Eugene Wigner, who described it as the unreasonable effectiveness of mathematics in the natural sciences. Wigner pointed out that there is no obvious reason why mathematical structures many of which were developed without any direct connection to physical reality, should turn out to describe that reality so accurately. It is as if the universe is written in a language that mathematics happens to capture perfectly. Or perhaps more intriguingly, it is as if mathematics is not just a tool for describing reality, but something more deeply connected to it. This idea is taken even further by Roger Penrose, a mathematician and physicist who has argued that mathematical structures may exist independently of the physical world. In Penrose's view, mathematical objects are not inventions of the human mind, but discoverers. They exist in a kind of abstract realm, and the physical universe reflects these underlying structures. According to this perspective, the reason mathematics works so well is that reality itself is fundamentally mathematical. This is a bold and somewhat philosophical position, but it is supported in part by the success of theories like quantum mechanics. The equations do not just approximate behavior, they seem to capture something essential about how the universe operates, and yet there is a tension here. While the mathematics is clear and precise, our interpretation of it is often less so. The wave function, for example, provides a complete description of a quantum system in mathematical terms. But what does it represent physically? Is it a real physical entity spread out across space? Is it simply a tool for calculating probabilities? Or is it something else entirely, something that does not have a direct analogue in the classical world? Different interpretations of quantum mechanics answer this question in different ways, and there is still no universal agreement. What is striking is that the mathematics continues to work regardless of how we interpret it. It is as if the equations are telling us the correct answers, even when we're not entirely sure what the questions mean. There is a quiet humility in that realization. It suggests that our intuitive understanding may not be the best guide at these scales. Instead, we rely on mathematical structures that have been tested and refined through experiment. To see how this plays out in practice, consider a simple quantum system, such as an electron confined within a small region of space. Using the Schrödinger equation, we can determine the allowed energy levels of the electron. These levels are discrete, not continuous, meaning the electron can only occupy specific states. When the electron transitions between these states, it emits or absorbs energy in the form of photons, with precise frequencies determined by the difference between energy levels. These predictions are not just theoretical, they are observed in experiments, such as the spectral lines of atoms, which have been measured with remarkable precision. In this way, the abstract mathematics connects directly to observable phenomena. It allows us to predict what we will see in the laboratory, even when the underlying processes are difficult to visualize. There is also something quietly reassuring about this. Even when our intuition struggles, the mathematics provides a reliable guide. It is like having a map of a landscape that is too complex to fully picture. We may not be able to visualize every detail, but we can still navigate with confidence. At the same time, the success of mathematics raises deeper questions about the nature of reality. Is the universe fundamentally mathematical, or is mathematics simply the most effective language we have found to describe it? It is possible that both perspectives contain some truth. Mathematics may be both a human creation and a reflection of deeper patterns in the world. What is clear is that in quantum physics, the role of mathematics is not just supportive, it is central. Without it, the theory would lose its predictive power. With it, we gain access to a level of precision and insight that would otherwise be impossible. And yet, despite this precision, the underlying meaning of the equations remains open to interpretation. This is part of what gives quantum physics its unique character. It is a theory that is both exact and mysterious, clear in its predictions yet ambiguous in its interpretation. And as we continue to explore its implications, the relationship between mathematics and reality becomes one of the most fascinating questions of all. A quiet reminder that sometimes understanding how something works is not the same as understanding what it is, and that even the most precise equations can point toward a deeper layer of mystery beneath the surface. As quantum theory continued to unfold, one idea began to stand out as both central and deeply unfamiliar: the idea that a system can exist in multiple states at the same time. This concept is known as superposition. In classical thinking, a system is always in one definite state. A light is either on or off. A coin is either heads or tails. An object is either here or there. But in quantum mechanics, the situation is more subtle. A particle can be in a combination of states simultaneously, not in the sense that it is rapidly switching between them, but in the sense that all possibilities are present together as part of a single, unified description. To make this more concrete, imagine an electron that can be found in one of two positions. In classical terms, it must be in one place or the other. But in quantum mechanics, the electron can exist in a superposition of both positions at once. The wave function describes this combined state, assigning a probability amplitude to each possibility. When a measurement is made, a single outcome is observed. But before that measurement, the system is not limited to one definite configuration. This idea can feel abstract, so physicists have often turned to thought experiments to illustrate it. One of the most famous examples was proposed by Erwin Schrödinger in the year 1935. He imagined a sealed box containing a cat, along with a small amount of radioactive material, a detector, and a mechanism that could release poison. If the radioactive atom decays, the detector triggers the release of poison, and the cat does not survive. If the atom does not decay, the cat remains alive. According to quantum mechanics, the radioactive atom exists in a superposition of decayed and not decayed states until it is observed. If this quantum description is extended to the entire system, then the cat itself would also exist in a superposition of alive and not alive states. Schrödinger introduced this example not to suggest that such a situation actually occurs in practice, but to highlight the difficulty of applying quantum ideas to everyday objects. It raises a simple but unsettling question. If superposition applies at the microscopic level, why do we not see it in the macroscopic world? Why are cats, chairs, and planets always found in definite states? Part of the answer lies in a concept known as quantum coherence. Coherence refers to the ability of a quantum system to maintain well-defined relationships between different parts of its wave function. When a system is coherent, the different components of its superposition can interfere with one another, producing observable effects like the interference pattern in the double-slit experiment. However, coherence is fragile. Quantum systems are constantly interacting with their surroundings. Even a small interaction, such as a collision with a single air molecule or the emission of a photon, can disrupt the delicate balance of the superposition. This process is known as decoherence. As a system interacts with its environment, the coherence between different states is lost, and the system begins to behave more like a classical object. The superposition does not necessarily disappear, but it becomes effectively unobservable. To get a sense of how quickly this happens, consider a microscopic particle in a controlled laboratory setting. It may maintain coherence for a measurable period of time, allowing experiments to observe quantum effects. But for larger objects, composed of trillions upon trillions of atoms, interactions with the environment occur constantly. The timescale for decoherence becomes extremely short, often far shorter than we can measure. This is why we do not see everyday objects in visible superpositions. The quantum behavior is still there in principle, but it is hidden beneath layers of interaction. And yet, modern experiments have begun to push these boundaries. Physicists have created superpositions involving increasingly large systems, including molecules made of dozens or even hundreds of atoms. In carefully controlled environments, these systems can exhibit interference patterns, demonstrating that superposition is not limited to the smallest particles. It is a general feature of quantum systems. This suggests that superposition may be more universal than it first appears. The distinction between quantum and classical behavior is not a sharp boundary, but a gradual transition influenced by the environment. Another intriguing perspective on superposition comes from the work of Yakir Aharonov. Aharonov has explored the idea of weak measurements, a technique that allows physicists to gather limited information about a system without fully collapsing its state. In a weak measurement, the interaction between the measuring device and the system is deliberately kept very small. This means that the measurement does not force the system into a single definite outcome in the usual way. Instead, it provides partial information, averaged over many repetitions of the experiment. These weak measurements have revealed surprising results, suggesting that quantum systems can exhibit properties that do not fit neatly into classical descriptions, even during the process of measurement. For example, certain experiments indicate that particles can appear to take paths that are not consistent with classical trajectories, reinforcing the idea that the underlying behavior is fundamentally different from anything we encounter in everyday life. These insights add another layer to our understanding of superposition. It is not simply a temporary state that disappears upon observation. It is a core aspect of how quantum systems exist and evolve. The challenge lies in how this aspect becomes hidden as systems grow larger and more complex. There is also a quiet philosophical dimension to all of this. If a system can exist in multiple states at once, what does that say about reality? Are all possibilities equally real until one is observed? Or is the superposition simply a tool for calculating probabilities? Different interpretations of quantum mechanics offer different answers, and there is still no universal agreement. But regardless of interpretation, the experimental evidence is clear. Superposition is not just a theoretical idea. It is a measurable, testable feature of the world at small scales. And as experimental techniques continue to improve, the boundary between quantum and classical behavior continues to shift. It is possible that what we think of as classical reality is not a separate domain, but an emergent one, arising from the underlying quantum structure through processes like decoherence. If that is the case, then the familiar world we experience is built upon a foundation that is far less definite than it appears, a foundation where possibilities overlap, where states combine, and where the act of measurement plays a crucial role in shaping what we observe. There is something quietly profound in that realization. The solidity of the world around us may not be as absolute as it seems. Beneath it lies a layer of reality that is fluid, probabilistic, and full of overlapping possibilities. And while we may not perceive this layer directly, its influence is present in everything. A reminder that even the most stable and familiar experiences are rooted in a deeper structure that is far more subtle and far more intriguing than we might have imagined. At some point, as these ideas settle in, a deeper question begins to emerge, not just how quantum systems behave, but why the act of observing them seems to change that behavior. This is often referred to as the measurement problem, and it sits at the very center of quantum theory. Up to this point, the wave function provides a smooth and continuous description of how a system evolves over time. It contains all the possible outcomes, each with its own probability amplitude. Left undisturbed, it follows a precise mathematical rule, evolving in a predictable way according to the Schrödinger equation. But something unusual happens when a measurement is made. Instead of continuing in a smooth, predictable evolution, the system appears to jump into a single, definite state. One outcome is observed, and all other possibilities seem to vanish. This transition is often described as the collapse of the wave function. The difficulty lies in understanding exactly what causes this collapse. Is it a physical process? Is it simply an update in our knowledge? Or is it something else entirely? One of the earliest and most influential attempts to address this question is known as the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg. In this interpretation, the wave function represents a set of potential outcomes, and the act of measurement selects one of those outcomes. Before measurement, it does not make sense to assign definite properties to the system. After measurement, a specific result is obtained. Bohr emphasized the importance of the experimental context. According to his view, the properties of a system are not independent of how they are measured. The measuring apparatus plays a crucial role in defining what can be observed. Heisenberg, in a similar spirit, suggested that the act of observation introduces a fundamental limit to what can be known, as captured by the uncertainty principle. Together, these ideas form a perspective in which the classical world and the quantum world are connected through measurement. The measuring device, which behaves classically, interacts with the quantum system and produces a definite outcome. This interpretation is practical and widely used. It provides a clear set of rules for making predictions and interpreting experiments, but it leaves certain questions unanswered. For example, what exactly counts as a measurement? Is it the interaction with a detector, the amplification of a signal, or the moment when a human observer becomes aware of the result? These questions led some physicists to explore more radical possibilities. One such approach is associated with John von Neumann and later Eugene Wigner, often referred to as the von Neumann-Wigner interpretation. In this view, the chain of interactions between a quantum system and a measuring device can be extended indefinitely. A particle interacts with a detector, the detector interacts with a recording device, the recording device interacts with a human observer, and so on. At each stage, the system could in principle remain in a superposition. So where does the collapse occur? Von Neumann showed that Mathematically, the boundary between quantum and classical systems can be shifted. There is no clear point in the physical chain where collapse must happen. Wigner took this idea further and proposed that consciousness itself might play a role. According to this perspective, it is the conscious observation that causes the wave function to collapse into a definite state. This idea is intriguing, but also controversial. It raises deep questions about the relationship between mind and matter, and it is not widely accepted as a physical explanation. Most modern physicists prefer interpretations that do not require consciousness to play a fundamental role. One of the most influential of these approaches is decoherence theory, developed in part by Wojciech Zurek. Decoherence provides a way to understand how classical behavior emerges from quantum systems through interaction with the environment. When a quantum system is isolated, it can maintain coherence, meaning that the different components of its wave function remain in a well-defined relationship. This allows for interference effects and superposition, but in practice, no system is perfectly isolated. Even the smallest interaction with the environment, such as a collision with a particle of air or a photon of light, can entangle the system with its surroundings. As this happens, the coherence between different parts of the wave function is lost. The system becomes effectively classical, not because the superposition disappears, but because it becomes spread out across the environment in a way that prevents interference from being observed. Decoherence explains why we do not see macroscopic superpositions in everyday life. It shows how the classical world can emerge naturally from quantum behavior. However, it does not fully solve the measurement problem. While decoherence explains the apparent disappearance of superpositions, it does not explain why a specific outcome is observed in a given experiment. The probabilities remain, but the selection of a single result still requires interpretation. This has led to alternative proposals that attempt to modify the theory itself. One example is the Ghirardi-Rimini-Weber theory, often abbreviated as GRW. In this approach, the collapse of the wave function is treated as a real, physical process. Instead of being triggered by measurement, collapse occurs spontaneously, with a small probability over time. For individual particles, this probability is extremely low, so their behavior remains largely governed by the standard quantum equations. But for larger systems composed of many particles, the probability of collapse increases, effectively suppressing macroscopic superpositions. This provides a possible explanation for why we do not observe large-scale quantum effects without requiring a special role for observers or measurement devices. GRW and similar objective collapse theories are still being explored and tested. They offer a different way of thinking about the transition from quantum to classical behavior. What is striking is that all of these approaches, despite their differences, are built on the same underlying mathematical framework. The equations of quantum mechanics remain unchanged. What varies is the interpretation of what those equations mean. This highlights a unique feature of quantum theory. It is not just a set of equations describing physical processes. It is also a collection of ideas about how those processes relate to observation, knowledge, and reality. The measurement problem sits at the intersection of these ideas. It reminds us that in quantum physics, the boundary between the observer and the observed is not always clear. The act of measurement is not simply a passive recording of what is already there. It is part of the process that defines what is observed. There is a quiet subtlety in this. We are not separate from the systems we study. Our interactions with them, however indirect, are woven into the outcomes we see. And yet, despite this complexity, the predictions of quantum mechanics remain extraordinarily accurate. Experiments continue to confirm its results, whether in the behavior of individual particles or in the operation of advanced technologies. So while the interpretation of measurement remains open to debate, the reliability of the theory itself is not in question. It works. And perhaps that is part of what makes it so fascinating, a theory that is both precise and uncertain, predictive and mysterious, clear in its calculations yet elusive in its meaning. As we continue to explore these ideas, the measurement problem remains a quiet reminder that understanding the universe is not always about finding definitive answers. Sometimes it is about learning to ask deeper questions. There is a particular feature of quantum physics that, more than almost anything else, challenges our sense of how the world should work. It is the idea that two particles can become linked in such a way that they no longer behave as separate objects. This phenomenon is known as quantum entanglement. To begin to understand it, Imagine creating a pair of particles in a way that ties their properties together. For example, suppose two particles are produced with a total spin that must add up to 0. Spin, in this context, is a quantum property that can take on discrete values, often described as either up or down. If one particle is later measured and found to have spin up, the other must have spin down. This relationship holds no matter how far apart the particles travel. At first, this may not seem too surprising. It could be explained by assuming that each particle carried its own hidden instruction from the moment they were created. But quantum mechanics predicts something more subtle. Before measurement, neither particle has a definite spin. Instead, the pair exists in a combined state, a superposition of both possibilities. It is only when one particle is measured that a specific outcome is obtained, and at that same moment, the state of the other particle becomes determined as well. What makes this particularly intriguing is that the correlation appears to hold even when the particles are separated by large distances. Measure one particle here, and the result of the other is instantly constrained, regardless of how far away it is. This idea was brought into sharp focus in the year 1935 through a paper written by Albert Einstein, Boris Podolsky, and Nathan Rosen. It is often referred to as the EPR paradox. Einstein and his colleagues were not trying to promote entanglement. They were, in fact, highlighting what they saw as a problem with quantum mechanics. They argued that if quantum theory were complete, it would imply what Einstein famously called spooky action at a distance. The apparent instantaneous connection between distant particles seemed to violate the principle of locality, which states that objects should only be influenced by their immediate surroundings. To resolve this, they suggested that quantum mechanics might be incomplete. Perhaps there were hidden variables, additional pieces of information that determined the outcomes in advance, restoring a sense of locality and realism. For a time, this remained a philosophical debate. There was no clear way to test whether quantum mechanics or hidden variable theories provided the correct description. That changed in the 1960s, when the physicist John Bell developed a way to distinguish between these possibilities. Bell derived a set of inequalities, now known as Bell's inequalities, that place limits on the strength of correlations that can be produced by any local hidden variable theory. Quantum mechanics predicts that these inequalities can be violated under certain conditions. In other words, if experiments show correlations stronger than Bell's limits, then no theory based on local hidden variables can fully explain the results. This transformed the discussion from a philosophical question into an experimental one, and over the following decades a series of experiments were carried out to test these predictions. One of the most significant sets of experiments was conducted by Alain Aspect and his team in the early 1980s. Aspect's experiments involved pairs of entangled photons, with their polarizations measured at separate locations. By carefully designing the setup and rapidly changing the measurement settings, the experiments were able to rule out many alternative explanations. The results were clear. The correlations between the entangled particles violated Bell's inequalities in agreement with the predictions of quantum mechanics. Since then, more refined experiments have been conducted, addressing potential loopholes and increasing the precision of the measurements. Research groups across the world, including those working with advanced quantum optics systems, have consistently confirmed these results. The evidence strongly suggests that the quantum description is correct, and that has profound implications. If the correlations cannot be explained by local hidden variables, then something about our classical picture of reality needs to be reconsidered. One possibility is that the principle of locality does not hold in the way we once thought. The behavior of entangled systems suggests that the properties of one particle are not entirely independent of another, even when they are separated by large distances. It is important to clarify what this does and does not mean. Entanglement does not allow information to be transmitted faster than the speed of light. The outcomes of measurements are still fundamentally random, and no usable signal can be sent through the entanglement alone. But the correlations are real, and they appear instantaneously. This creates a subtle tension with our usual understanding of space and time. In classical physics, interactions are local. Forces act through fields that propagate at finite speeds. Objects influence one another through direct contact or through signals that travel across space. Entanglement suggests a different kind of connection, one that is not mediated by a signal in the usual sense, and not limited by distance in the same way. It is as if the two particles form a single system, even when they are far apart. This idea challenges the notion that reality is composed of independent, localized parts. Instead, it points toward a more interconnected structure, where relationships between systems play a fundamental role. Some physicists have described entanglement as the defining feature of quantum mechanics. Erwin Schrödinger himself emphasized its importance, noting that it represents the characteristic trait of quantum theory, the one that distinguishes it most clearly from classical physics. There is also a growing sense that entanglement may not just be a curious feature, but a foundational one. In modern research, particularly in the field of quantum information, entanglement is treated as a resource. It can be used for tasks such as quantum communication, quantum cryptography, and quantum computing. Experiments have demonstrated entanglement over increasingly large distances, including satellite-based systems that link particles across hundreds or even thousands of kilometers. These advances show that entanglement is not just a theoretical concept. It is something that can be created, controlled, and used in practical applications. At the same time, its deeper meaning remains open to interpretation. Does entanglement imply that space itself is not fundamental? Does it suggest that reality is inherently non-local? Or is it pointing toward an even deeper structure that we do not yet fully understand? There is no single answer that is universally accepted, but what is clear is that entanglement forces us to rethink some of our most basic assumptions. The idea that objects are separate, the idea that distance limits interaction, the idea that properties exist independently of observation. All of these concepts become less certain in the presence of entanglement, and yet, the phenomenon itself is not chaotic or inconsistent. It follows precise mathematical rules. It produces reliable, testable predictions. It fits seamlessly within the broader framework of quantum mechanics. This combination of precision and strangeness is part of what makes quantum physics so compelling. It shows us that the universe can behave in ways that are both deeply unfamiliar and rigorously consistent. And as we continue to explore entanglement, it becomes increasingly clear that the world may be more connected than it appears. Not just in the obvious ways through forces and interactions, but in ways that are more subtle, more abstract, and perhaps more fundamental. A quiet reminder that beneath the surface of everyday experience, the structure of reality may be woven together in ways that challenge our intuition, but continue to reveal themselves, one experiment at a time. As the implications of entanglement began to settle in, a quiet shift took place in how physicists started to think about it. At first, entanglement was treated as a curious feature of quantum systems, something unusual, perhaps even inconvenient, that had to be accounted for. But over time, that perspective began to change. Rather than being a side effect, entanglement started to look more like a central ingredient, not just something that happens within the universe, but something that might help define its structure. To see how this idea develops, it helps to take a step back and consider what entanglement actually represents. When two particles are entangled, their properties are not independent. The system must be described as a whole. Even if the particles are separated by large distances, their states remain linked in a way that cannot be reduced to individual parts. This suggests that the fundamental building blocks of reality may not be isolated objects but relationships. And if relationships are primary, then perhaps space itself, the distance between things, is not as fundamental as it appears. This is where some of the more modern and speculative ideas in physics begin to emerge. One of the most intriguing proposals comes from the work of Juan Maldacena, a theoretical physicist who has explored deep connections between quantum mechanics and gravity. In collaboration with Leonard Susskind, Maldacena proposed a bold idea known as the ER equals EPR conjecture. The name refers to two seemingly unrelated concepts. EPR, as we have seen, stands for Einstein, Podolsky, and Rosen, and describes quantum entanglement. ER refers to Einstein and Rosen, who in the year 1935 studied solutions to the equations of general relativity that describe what are now known as wormholes, or Einstein-Rosen bridges. A wormhole is a theoretical structure that connects two separate regions of space-time, forming a kind of shortcut between them. The ER equals EPR conjecture suggests that these two ideas may be connected. In simple terms, it proposes that entangled particles could be linked by microscopic wormholes, not in a way that allows travel or communication, but as a geometric representation of their connection. This does not mean that every pair of entangled particles literally forms a traversable tunnel through space. Rather, It suggests that the mathematical description of entanglement may be closely related to the geometry of space-time itself. If this idea is correct, then entanglement is not just a feature of particles within space. It may be part of what gives rise to space in the first place. This leads to a profound possibility. Space-time, the very fabric of the universe, may be an emergent phenomenon arising from deeper quantum relationships. Instead of space being a fixed stage on which events occur, it could be something that is built from patterns of entanglement. There is a certain elegance in this idea. It suggests that the connections we observe in quantum systems are not anomalies, but hints of a deeper structure. A structure in which geometry and information are closely intertwined. While these ideas are still being explored and are not yet fully established, they are part of a growing effort to unify quantum mechanics with general relativity, Einstein's theory of gravity. This remains one of the central challenges in modern physics. Quantum mechanics describes the behavior of the very small. General relativity describes the structure of space-time on the larger scales. Both theories are highly successful in their respective domains, but they are not easily combined into a single, consistent framework. Entanglement may provide a bridge between them. By studying how quantum systems encode information and how that information relates to geometry, physicists hope to uncover a deeper understanding of how the universe is put together. At the same time, experimental work continues to push the boundaries of what can be observed. Physicists such as Nicholas Giesen have conducted experiments demonstrating entanglement over increasingly large distances. In some cases, entangled photons have been transmitted across many kilometers of optical fiber, maintaining their correlations despite environmental challenges. More recently, satellite-based experiments have extended these distances even further, linking particles across hundreds or even thousands of kilometers. These experiments confirm that entanglement is not limited to small, isolated systems. It can persist across scales that begin to approach those of everyday experience. And yet, even at these distances, the fundamental behavior remains the same. The correlations are preserved. The predictions of quantum mechanics hold. The strange connection between particles does not fade with distance. This reinforces the idea that entanglement is not a fragile or marginal effect. It is a robust and fundamental feature of the world. As these insights accumulate, a new picture begins to form, one in which the universe is not simply a collection of independent objects arranged in space, but a network of relationships woven together through patterns of entanglement. In this picture, distance may not be the primary measure of separation. Instead, the strength of entanglement between systems could play a more fundamental role. Two regions of space that are strongly entangled might be considered close in a deeper sense, even if they appear far apart in classical terms. This idea is still being developed, but it has already influenced research in areas such as quantum gravity and cosmology. Some models suggest that the large-scale structure of the universe, including the behavior of black holes and the expansion of space, may be linked to underlying patterns of quantum entanglement. There is even speculation that the smooth geometry of space-time emerges from a more discrete quantum foundation, much like a continuous image emerges from a grid of pixels. If that is the case, then entanglement could be the thread that holds this structure together, a kind of hidden connectivity that shapes the fabric of reality from within. There is something quietly remarkable about this shift in perspective. What began as a puzzling feature of quantum experiments is now being considered as a possible foundation for the entire universe. And while many of these ideas are still under investigation, they reflect a broader trend in physics, a movement away from thinking in terms of isolated objects and toward thinking in terms of relationships and information. This does not make the universe less real or less structured. If anything, it reveals a deeper level of organization, one that is not immediately visible, but becomes apparent through careful study and experimentation. And as we continue to explore these connections, the sense of quantum weirdness begins to take on a different character. It is no longer just a collection of strange behaviors. It is a window into a deeper layer of reality, a layer where space, time, and connection are not fixed and separate, but emerge together from a more fundamental network. A network that we are only just beginning to understand. By this point, a quiet tension has begun to build. On one hand, the quantum world appears fluid, probabilistic, and full of overlapping possibilities. On the other, The world we experience feels solid, stable, and well-defined. Objects sit in definite places, events unfold in a clear sequence. A cup rests on a table, not in a superposition of locations across the room. So how do these two pictures fit together? How does a universe built on uncertainty give rise to the certainty we experience every day? This question leads us into the idea of emergence. Emergence is the concept that complex large-scale behavior can arise from simpler underlying rules, often in ways that are not immediately obvious. It appears in many areas of science, from the formation of galaxies to the behavior of biological systems. In the context of quantum physics, emergence helps explain how classical reality arises from quantum foundations. At the smaller scales, systems are described by wave functions, probabilities, and superpositions. But as systems grow larger and interact with their surroundings, their behavior begins to change. The key process behind this transition is known as decoherence. As we touched on earlier, decoherence occurs when a quantum system interacts with its environment. These interactions cause the system to become entangled with countless degrees of freedom in its surroundings, such as air molecules, photons, and other particles. This entanglement spreads the information about the system into the environment, effectively dispersing the coherence that allows quantum superpositions to produce interference. The result is that the system begins to behave as if it were in a definite state, even though, at a deeper level, the full quantum description still exists. To understand this more intuitively, imagine trying to keep a delicate pattern intact on the surface of a still pond. If the water remains undisturbed, the pattern can persist. But as soon as even small ripples appear, the pattern becomes distorted and eventually disappears. In a similar way, quantum coherence is easily disrupted by interactions with the environment. For microscopic systems in carefully controlled laboratory conditions, coherence can be maintained long enough to observe quantum effects. But for larger systems, coherence is lost extremely quickly. This is why everyday objects appear classical. They are constantly interacting with their environment, and these interactions suppress the observable effects of superposition. However, decoherence alone does not fully explain why we observe specific outcomes. It tells us why interference disappears, but it does not explain why one particular result is realized instead of another. This is where an idea known as quantum Darwinism, developed by Wojciech Zurek, offers an additional perspective. Quantum Darwinism extends the concept of decoherence by focusing on how information about a system is distributed into the environment. When a quantum system interacts with its surroundings, certain properties of the system become imprinted onto the environment in multiple copies. For example, photons scattering off an object carry information about its position. These scattered photons can be detected by many observers independently, each receiving consistent information about the system. Over time, only certain states of the system are able to leave stable, redundant imprints in the environment. These states are known as pointer states. Pointer states are robust against decoherence and can be observed repeatedly without being destroyed. In this way, the environment acts as a kind of filter, selecting which aspects of a quantum system become part of our shared classical reality. This process is referred to as quantum Darwinism because it resembles a form of natural selection. Out of many possible quantum states, only those that are stable and capable of spreading information effectively survive and become observable. The rest remain hidden, unable to leave a lasting imprint. This provides a way to understand how objective reality emerges. It is not that the quantum world disappears, it is that certain features become amplified and accessible, while others fade into the background. The world we experience is shaped by the information that is most widely available. This leads to an interesting perspective. Reality, as we perceive it, may not be a direct reflection of the underlying quantum state. Instead, it may be a kind of consensus, built from the information that is most easily shared and observed. In this sense, reality is layered. At the deepest level, there is the full quantum description, with all its superpositions and probabilities. At a higher level, there is the classical world, where objects have definite properties and behave in predictable ways. These layers are not separate in the way that two different worlds might be. They are connected, with the classical layer emerging from the quantum one through processes like decoherence and information selection. To bring this back to everyday experience, consider something as simple as a chair. At the quantum level, the atoms that make up the chair are described by wave functions. Their positions are not perfectly defined, and they exist within a range of possibilities. But because the chair is made up of an enormous number of particles, and because it is constantly interacting with its environment, these uncertainties are effectively averaged out. The chair appears solid, stable, and well-defined. You can sit on it without worrying that it might suddenly dissolve into a cloud of probabilities. This does not mean that the quantum description is irrelevant. It is still the foundation of the chair's behavior. But at the scale of everyday experience, the classical description is more practical and accurate. It is an emergent layer built upon the underlying quantum structure. There is something quietly reassuring in this. The strange and unfamiliar aspects of quantum physics do not disrupt the world we experience. They are woven into it, providing the foundation upon which classical reality is built. At the same time, this perspective invites us to think differently about what we mean by reality. If what we observe depends on how information is distributed and selected, then reality may not be a single, fixed entity. It may be a dynamic process, shaped by interactions and relationships. A process that becomes more stable and predictable as systems grow larger and more connected. And yet, beneath this stability, the quantum layer remains. A subtle reminder that even the most solid and familiar objects are rooted in a deeper, more fluid structure. As these ideas settle in, the gap between the quantum and classical worlds begins to feel a little less like a divide and more like a transition. A gradual shift from possibility to certainty, from coherence to decoherence, from the many to the one. And in that transition, we begin to see how the strange behavior of the quantum world gives rise to the calm and consistent reality we experience every day. By now, it becomes clear that quantum mechanics is not just a theory about how the world behaves, it is also a theory that invites interpretation. The mathematical framework is precise and widely agreed upon. It tells us how to calculate probabilities, how systems evolve, and how to predict experimental outcomes with remarkable accuracy. But when it comes to understanding what the theory actually means, the picture becomes far less settled. Different interpretations offer different ways of thinking about the same underlying equations. They do not change the predictions, but they change the story we tell about reality. And in some cases, those stories can be quite different from one another. One of the most well-known interpretations is the many worlds interpretation, introduced by Hugh Everett in the year 1957. Everett proposed a radical idea. Instead of the wave function collapsing into a single outcome during measurement, it never collapses at all. Instead, all possible outcomes of a quantum event continue to exist, each in its own branch of reality. When a measurement is made, the universe effectively splits into multiple versions, one for each possible result. In one branch, a particle is found in one position. In another branch, it is found somewhere else. Each branch is equally real, but they no longer interact with one another. From the perspective of an observer within one branch, it appears as though a single outcome has occurred. But from a broader perspective, all outcomes exist simultaneously. This interpretation removes the need for wave function collapse. The evolution of the system remains smooth and continuous at all times. It is a mathematically clean solution, but it comes with a striking implication. Reality may be constantly branching into a vast number of parallel worlds. These worlds are not accessible to one another, and there is no way to observe them directly. Yet according to this interpretation, they are just as real as the one we experience. For some, this idea feels extravagant. For others, it is a natural consequence of taking the equations seriously. It is worth noting that Everett's work was initially met with skepticism, and it took many years before it gained wider attention. Today, it remains one of the most discussed interpretations in quantum foundations. A related but distinct idea is known as many interacting worlds, developed by researchers including Hall, Deckert, and Wiseman. In this approach, instead of a single wave function describing all possibilities, there are many classical worlds that exist in parallel. These worlds are not completely independent. They interact with one another in subtle ways, and these interactions give rise to quantum effects. In this picture, quantum behavior emerges from the collective dynamics of many interacting classical systems. It is an attempt to retain a more intuitive classical description while still accounting for the observed phenomena. Like many worlds, it suggests that our familiar experience is just one of many possible realities, but it introduces interaction between these realities rather than complete separation. Another perspective takes a different approach altogether. Relational quantum mechanics, developed by Carlo Rovelli, focuses on the idea that physical properties are not absolute, but relative. In this interpretation, the state of a system is always defined in relation to another system. There is no single, observer-independent description of reality. For example, a particle may have a definite position relative to one observer, while remaining in a superposition relative to another. This does not imply a contradiction. Instead, it reflects the fact that different observers can have different, equally valid descriptions of the same system. In this view, reality is not a collection of fixed properties, but a network of relationships. What exists are interactions, and the properties of systems emerge from those interactions. This interpretation aligns naturally with some of the earlier ideas about entanglement and information, where relationships between systems play a central role. It also offers a way to think about quantum phenomena without requiring a special role for measurement or collapse. Then there are more controversial ideas, such as superdeterminism. Superdeterminism challenges one of the key assumptions underlying Bell's theorem, namely that measurement settings can be chosen independently of the systems being measured. In standard experiments, it is assumed that the choice of measurement settings is free and not influenced by hidden variables associated with the particles. Superdeterminism suggests that this assumption may not hold. According to this view, all events in the universe, including the choices made by experimenters, are determined by underlying conditions. These conditions could, in principle, correlate the measurement settings with the properties of the particles in such a way that the observed correlations are explained without requiring non-local effects. Gerard 't Hooft, a Nobel Prize-winning physicist, has explored this possibility in recent years. While superdeterminism offers a way to preserve locality, it comes at a cost. It challenges the idea of free choice in experiments and raises questions about the independence of scientific testing. If measurement settings are not truly independent, then the interpretation of experimental results becomes more complicated. For this reason, superdeterminism remains a subject of debate and is not widely adopted as a mainstream explanation. What is striking about all of these interpretations is that they share the same mathematical foundation. The equations of quantum mechanics do not change. The predictions remain the same. Experiments cannot currently distinguish between these interpretations in a definitive way. This creates a unique situation in science. Multiple, very different descriptions of reality are all consistent with the same set of observations. It is as if we have a map that accurately predicts every destination, but we are still unsure what the landscape truly looks like. This does not mean that all interpretations are equally plausible or equally useful. Each comes with its own strengths, challenges, and philosophical implications. Some prioritize mathematical simplicity, some aim for intuitive clarity, some emphasize the role of information and relationships, and the discussion is ongoing. Physicists continue to explore these ideas, looking for ways to test them, refine them, or connect them to deeper theories. There is also a growing recognition that the answer may not lie in choosing a single interpretation, but in developing a new framework that goes beyond the current ones. A framework that can unify quantum mechanics with gravity and provide a clearer picture of how reality is structured at the most fundamental level. For now, the situation remains open, and there is something quietly fascinating about that. In many areas of science, questions are resolved as more data becomes available. Theories are refined, and uncertainty gradually decreases. In quantum mechanics, the data is already extremely precise. The theory works exceptionally well, yet the meaning of the theory remains in some sense unresolved. This does not weaken the science. If anything, it highlights its depth. It shows that understanding the universe is not just about making accurate predictions. It is also about finding ways to interpret those predictions to connect them to a broader picture of reality. And sometimes that process takes time. As these interpretations continue to be explored, they offer different ways of thinking about the same underlying phenomena, different lenses through which to view a world that is, at its core, both precise and mysterious. A world that continues to invite us to question not just how things happen, but what it really means for something to be real. At this point, it is worth stepping back for a moment and asking a slightly different question. Why does all of this feel so strange? The equations of quantum mechanics are consistent, the experiments are repeatable, the predictions are accurate, and yet, when we try to form an intuitive picture of what is happening, something always seems slightly out of place. Particles behaving like waves, objects existing in multiple states at once, connections that appear to ignore distance. It can feel as though the theory is deliberately resisting our attempts to understand it. But perhaps the difficulty does not lie in the theory itself. Perhaps it lies in us. Human intuition is not a general-purpose tool for understanding all aspects of reality. It is a product of evolution, shaped by the environments in which our ancestors lived. For millions of years, survival depended on navigating a world of moderate sizes and speeds. Objects were large enough to see and touch. Causes followed effects in predictable ways. Distances were measured in meters, not in atomic scales or light years. In this environment, it made sense to think of objects as solid, continuous and independent. It made sense to expect that things would have definite positions and trajectories. These intuitions became deeply embedded in how we perceive and interpret the world. But quantum systems operate far outside this range of experience. An electron is roughly 1/10,000th the size of an atom. Its behavior is governed by Planck's constant, a number so small that its effects are invisible at everyday scales. The rules that apply at this level are not the same as those that apply to falling objects or moving vehicles, and yet we try to understand them using the same mental models. It is a bit like trying to understand the behavior of the ocean by studying a single drop of water under a microscope. The context is completely different, and the tools we're using may not be suited to the task. This idea has been explored in more formal terms by cognitive scientists such as Donald Hoffman. Hoffman has proposed that our perception of reality is not a direct representation of the world as it truly is. Instead, it is more like an interface, designed to help us interact with our environment efficiently. In his view, evolution favors perceptions that are useful, not necessarily those that are accurate. To illustrate this, imagine a simple graphical interface on a computer screen. Icons represent files, folders, and applications. These icons are not literal representations of the underlying processes in the computer. They are simplified symbols that allow us to interact with the system without needing to understand its internal workings. In a similar way, our sensory experiences may be providing us with a simplified interface to reality. We see objects as solid and well-defined because that is useful for navigation and survival. We experience time as flowing in a single direction because that aligns with how processes unfold at our scale. But beneath this interface, the underlying structure may be very different. Quantum mechanics could be revealing aspects of that deeper structure, and when we encounter it, it feels strange, not because it is inherently illogical, but because it does not match the simplified models our minds have constructed. There is also a question of scale. At the macroscopic level, many quantum effects average out. The behavior of large numbers of particles tends to produce stable, predictable patterns. This is why classical physics works so well for everyday phenomena, but at the microscopic level, individual events become significant. Fluctuations that would be negligible in large systems become dominant. It is like the difference between observing the overall motion of a crowd and tracking the movement of a single individual. The crowd appears smooth and continuous. The individual's path is more irregular and difficult to predict. Quantum physics focuses on the individual level, where uncertainty and probability play a central role. Another factor is language. The words we use, such as particle, wave, position, and trajectory, are rooted in classical experience. They carry assumptions that may not apply at the quantum level. When we say that an electron behaves like a wave, we are borrowing a familiar concept to describe something that is not quite the same. This can create a sense of contradiction, even when the underlying mathematics is consistent. It is a reminder that language can shape our perception of a problem, sometimes in ways that make it harder to see clearly. There is a gentle kind of humour in this. The universe is not necessarily behaving strangely. It is simply not following the rules we expected. And those expectations were shaped by a very specific set of conditions. If our senses had evolved to operate at atomic scales, perhaps quantum behaviour would feel entirely natural. Perhaps it would be classical physics that seemed odd, with its smooth trajectories and continuous motion. This shift in perspective can be helpful. It allows us to see quantum weirdness not as a flaw in the theory, but as a reflection of the limits of our intuition. The theory itself is consistent, precise, and supported by a vast body of experimental evidence. The challenge lies in reconciling it with the mental models we use to understand the world. And that is not always easy. but it is also part of what makes science so interesting. It pushes us to go beyond our immediate experience, to develop new ways of thinking, to question assumptions that may have seemed obvious. In doing so, it expands our understanding, not just of the universe, but of our own perception. As these ideas settle in, the sense of strangeness begins to shift. It becomes less about the behavior of the quantum world and more about the relationship between that world and the way we perceive it, a mismatch between reality and intuition. And perhaps, over time, as we become more familiar with these concepts, that mismatch begins to feel a little less like confusion and a little more like discovery. It is easy to think of quantum physics as something distant and abstract, a theory that lives in equations, laboratories, and philosophical debates. But in a quieter, more practical sense, it is already woven into the fabric of everyday life. Many of the technologies that shape the modern world rely directly on quantum principles, even if we rarely notice it. One of the most important examples is the semiconductor. Semiconductors are the foundation of modern electronics. They are used in transistors, which are the building blocks of computers, smartphones, and countless other devices. The behavior of semiconductors cannot be explained using classical physics alone. It depends on the quantum properties of electrons in solids, particularly the concept of energy bands. In a solid material, electrons do not occupy arbitrary energy levels. Instead, they are restricted to specific ranges, known as bands. Between these bands are gaps where no electron states are allowed. In conductors, such as metals, the bands overlap, allowing electrons to move freely. In insulators, the gap between bands is large, preventing electron movement. Semiconductors sit in between. Their band gap is small enough that electrons can be encouraged to move under the right conditions, such as the application of an electric field or the introduction of impurities through a process known as doping. This controlled movement of electrons allows semiconductors to act as switches, turning electrical currents on and off with remarkable precision. Without this quantum behavior, modern computing would not exist in its current form. Another familiar technology grounded in quantum physics is the laser. The word laser stands for light amplification by stimulated emission of radiation. The key process here is stimulated emission, first described by Albert Einstein in the early 20th century. In an atom, electrons can occupy discrete energy levels. When an electron transitions from a higher energy level to a lower one, it emits a photon of light with a specific frequency. In stimulated emission, an incoming photon can trigger an excited electron to drop to a lower energy level, emitting a second photon that is identical to the first in both frequency and direction. This process can be described as follows. An incoming photon stimulates an excited atom to emit a second photon with the same energy, phase, and direction. When this process is repeated within a carefully designed system, it produces a coherent beam of light where all the photons are aligned. Lasers are used in a wide range of applications, from optical communication and medical devices to barcode scanners and everyday consumer electronics. They are a direct result of quantum principles applied in a controlled and practical way. More recently, attention has turned to a new kind of technology that takes quantum behavior even further: quantum computing. Unlike classical computers, which use bits that can be either 0 or 1, quantum computers use quantum bits or qubits. A qubit can exist in a superposition of states, meaning it can represent both 0 and 1 simultaneously, in a probabilistic sense. In addition, qubits can become entangled with one another, creating correlations that allow for new kinds of computation. These properties enable quantum computers to perform certain calculations more efficiently than classical computers. The idea of quantum computation was developed in part by David Deutsch in the 1980s. He proposed that a quantum system could be used to simulate other quantum systems, potentially solving problems that are intractable for classical machines. Since then, the field has grown rapidly, with research groups and companies working to build practical quantum computers. In recent years, organizations such as Google and IBM have demonstrated what is sometimes referred to as quantum supremacy. This term describes the point at which a quantum computer performs a specific task that would be extremely difficult for a classical computer to replicate. For example, in the year 2019, Google reported that its quantum processor had completed a particular calculation in a matter of minutes, a task that would take a classical supercomputer much longer. While these demonstrations are still limited in scope, they represent an important step forward. Quantum computers are not yet ready to replace classical systems for most tasks, but they hold promise for areas such as cryptography, optimization, and the simulation of complex physical systems. Another area where quantum principles are being applied is communication. Quantum communication takes advantage of properties such as entanglement and the no-cloning theorem, which states that it is not possible to create an exact copy of an unknown quantum state. This leads to the development of quantum cryptography, where secure communication can be achieved by encoding information in quantum states. Any attempt to intercept or measure the communication would disturb the system, revealing the presence of an eavesdropper. This approach has already been tested in real-world systems. One notable example involves satellite-based quantum communication experiments, such as those conducted with the Messius satellite. These experiments have demonstrated the transmission of entangled photons over distances of hundreds to thousands of kilometers. This opens the possibility of global quantum communication networks, where information can be transmitted securely across vast distances. What is striking about all of these technologies is that they rely on the very features of quantum mechanics that initially seemed so strange. Superposition, entanglement, quantization, and probability are not just abstract concepts, they are practical tools. They allow us to build devices that process information, generate light, and transmit signals in ways that would not be possible using classical physics alone. In this sense, the weirdness of quantum physics is not a barrier, it is a resource, something that can be harnessed and applied in creative ways. At the same time, these technologies serve as a reminder of how deeply quantum mechanics is embedded in the world around us. Even when we are not thinking about it, even when we are simply using a device or turning on a light, we are interacting with systems that depend on quantum principles. There is something quietly remarkable about that. A theory that once seemed abstract and puzzling has become the foundation for much of modern technology. And yet, despite this practical success, the deeper questions remain. We can build devices that rely on quantum behavior, even if we do not fully agree on what that behavior means. We can use the theory with great precision, even as we continue to explore its interpretation. This combination of utility and mystery is part of what makes quantum physics so unique. It is both a powerful tool and an ongoing exploration, a field that continues to shape the modern world, while still inviting us to look deeper and ask more fundamental questions about the nature of reality. As far as quantum mechanics has taken us, there is still a sense that something is missing. The theory is extraordinarily successful. It describes atoms, particles, and interactions with remarkable precision. It underpins much of modern technology and has been tested in countless experiments. And yet, when we look at the universe on its largest scales, a different theory takes over. General relativity, developed by Albert Einstein, describes gravity not as a force, but as the curvature of space-time. Massive objects bend the geometry around them, and this curvature guides the motion of other objects. It is a beautiful and powerful framework capable of explaining the motion of planets, the behavior of stars, and the expansion of the universe itself. But here is the difficulty. Quantum mechanics and general relativity are both highly successful, and they do not fit together easily. Quantum mechanics describes a world of probabilities, discrete quantities, and superpositions. General relativity describes a smooth, continuous spacetime, where geometry itself evolves according to precise equations. When physicists try to combine these two frameworks, inconsistencies appear. In situations where both quantum effects and strong gravitational fields are important, such as inside black holes or at the very beginning of the universe, neither theory alone is sufficient. This has led to one of the central challenges in modern physics: to develop a theory of quantum gravity, a framework that unifies quantum mechanics and general relativity into a single, consistent description. Several approaches have been proposed, each offering a different perspective on how this might be achieved. One of these is loop quantum gravity, developed by physicists including Carlo Rovelli and Lee Smolin. In this approach, spacetime itself is not continuous but quantized. Instead of being a smooth fabric, it is made up of tiny discrete units, often described as loops or networks. These structures, known as spin networks, define the geometry of space at the smallest scales. In loop quantum gravity, areas and volumes come in discrete amounts, much like energy levels in quantum mechanics. This suggests that space itself has a granular structure, with the smallest possible unit often associated with the Planck length, which is approximately 1.6 times 10 to the minus 35 meters. At scales larger than this, space-time appears smooth, just as a digital image appears continuous when viewed from a distance, but at the deepest level it may be composed of these fundamental building blocks. This approach has the advantage of staying close to the principles of general relativity, while incorporating quantum ideas. However, it is still a developing theory, and many questions remain about how it connects to observable phenomena. Another major approach is string theory, which takes a very different path. In string theory, the fundamental constituents of the universe are not point particles, but tiny one-dimensional objects known as strings. These strings can vibrate in different ways, and each mode of vibration corresponds to a different particle. In this framework, particles such as electrons and quarks are not separate entities, but different expressions of the same underlying structure. String theory also naturally includes gravity, as one of the vibrational modes corresponds to a particle known as the graviton, which would mediate the gravitational interaction. One of the most striking features of string theory is that it requires additional dimensions of space beyond the familiar 3. Depending on the version of the theory, there may be 10 or even 11 dimensions in total. The extra dimensions are thought to be compactified, meaning they are curled up at extremely small scales and not directly observable. Physicists such as Edward Witten have played a central role in developing and unifying different versions of string theory, revealing deep mathematical connections between them. While string theory is mathematically rich and has led to many insights, it also faces challenges. It is difficult to test experimentally, as the energy scales involved are far beyond what current technology can achieve. This has led to ongoing debates about its role as a physical theory versus a mathematical framework. Alongside these approaches, another idea has emerged that connects quantum mechanics, gravity, and information in a surprising way. This is the holographic principle, developed by physicists such as Gerard 't Hooft and Leonard Susskind. The holographic principle suggests that the information contained within a volume of space can be described by information on the boundary of that space. In other words, a 3-dimensional region could be fully encoded on a 2-dimensional surface. This idea was inspired in part by studies of black holes, where the entropy or information content of a black hole appears to be proportional to the area of its event horizon, rather than its volume. This challenges our usual understanding of space. It suggests that the fundamental description of the universe may not reside in the 3-dimensional space we experience, but on a lower dimensional boundary. In certain theoretical models, such as the ADS-CFT correspondence developed by Juan Maldacena, this idea is made precise, showing a duality between a gravitational theory in one space and a quantum field theory on its boundary. This connection has provided new tools for exploring quantum gravity and has deepened our understanding of how space-time and quantum information may be related. Taken together, these approaches point toward a common theme: the idea that space-time, particles, and forces may all emerge from a deeper, more fundamental structure, a structure that is not yet fully understood. Despite decades of research, a complete theory of quantum gravity remains out of reach. There are many promising ideas, many partial insights, but no single framework that has been universally accepted and experimentally confirmed, and yet this is not a failure. It is a reflection of how far we have come and how much remains to be explored. Physics has always progressed by pushing against the boundaries of understanding, by identifying where current theories fall short and searching for new ways to extend them. The edge of understanding is not a place of confusion, but a place of discovery. It is where new ideas begin to take shape, where familiar concepts are re-examined, and where the structure of reality is explored in greater depth. There is something quietly exciting about this, the realization that even now, with all that we have learned, the universe still holds secrets, that the theories we have developed, as powerful as they are, may be part of a larger picture that we are only beginning to see. And as we continue to explore that picture, we are reminded that understanding is not a final destination. It is an ongoing journey, one that invites us to look deeper, think more carefully, and remain open to the possibility that the universe may be even more subtle and intricate than we have imagined.